much mass of consumables you need for long missions and scale them down to our 33 days. We found the total mass of the ship. The propulsion units we based on the Falcon 9 upper stage because it's cheap, it's commercial, it's reliable, and it's designed to operate in a vacuum. We're not suggesting that this exact rocket would be used, for one thing because it uses kerosene, but its basic proportions were useful to be scaled up to our needs. So to find the number of rockets we need, we just set equal to the mass ratio, just its definition, which is the fueled mass to the unfueled mass. And we found that the propulsion unit would need to have as much fuel and dry mass as about 3 upper stages. And that let us find the total mass of the system. Now, since we have the mass, we could get the cost. We assumed to use the Falcon 9 and Falcon 9 Heavy as the cheapest rockets and probably the most reliable by then, so they would have had dozens and dozens of launches. The crew and service modules can launch on one Falcon 9, the propulsion module on another. The fuel can launch on some of the heavy rockets and also one of the normal rockets. This leaves us plenty of extra payload mass for the fuel tank structures because we assumed that the fuel would just be by itself without any fuel tank structures in the original estimation. So the total bill for launch services was $528 million. That doesn't include astronaut launch services because we assumed they would have already spent weeks in space on a station to work out their spacings or any other matters. This design would be highly reusable, even though only about 1/7 of the mass would come back to low Earth orbit at the end of the journey. That would represent almost all the cost of the hardware because we assumed a single-stage propulsion unit. So this craft would just be refurbished, tested, refueled, and then it could go to another asteroid or to Mars. It could go pretty much anywhere.
And so we need to take into account one other factor, and that's that of interplanetary particles and radiation, because we'll be moving out of the radius of Earth's magnetosphere, which protects all craft within it to a degree from things like cosmic rays. And so we could use this mission as a test to see how equipment and other hardware would hold up to the cosmic rays, to the radiation. And since the mission is relatively short, about a month, the risk is relatively low, but we could still see how it's affected.
Also, the Sundancer unit includes a radiation shield. Since these inflatable modules are probably the future of in-space habitation, it would be important to know how they respond to radiation in a more intense environment than within the veil. The conclusion of our project is that a manned flight to an asteroid is possible and feasible. It's in fact much easier than previous estimations had found, especially this single journey. Current technology could do the journey for much less cost than we're spending on some other programs now, but in 18 years it will likely be even cheaper and easier. And the most important aspect of the mission is that it's a stepping stone for a manned mission to Mars. It would give us data on how people perform very far away from Earth, and with more significant communications delay, about 6 seconds one way than on the Moon. And we're trying to do this now in things like the Mars 500, but of course this would be much more realistic than that. Thanks for listening to our presentation. We think that an asteroid mission is possible, and you will want NASA to do that as we take your questions.
You may have said how far away did they get at the asteroid?
It's about 6 light seconds. So the closest was 0.0123 AU.
What was that?
About 0.01 AU. Very close.
What kind of asteroid was this? Was it a nickel iron or was it carbonaceous? Do you know?
We actually don't know much about this asteroid. One of the things we want to do would be to send a robotic precursor, both to learn more about it and to identify formations for the astronauts to study when they're there. So we wouldn't just send the crew to it before we knew exactly what was there. So,
could you expand a little bit on what you would do in the vicinity of the asteroid as you go into the...
Yes. Well, we figured that the craft would just hover next to the asteroid, wouldn't land on it. There's not enough gravity to do that. The astronauts would first use the manned maneuvering units to establish some kind of like rope system on the asteroid. They fire spikes into it and string cables so they could hold onto them instead of using up the gas in the manned maneuvering units. They'd probably drill into the asteroid. They'd take lots of pictures and measurements and perhaps relay those back to the Earth, and the Earth would tell them which of the sites would be the most promising to collect samples and bring back to Earth practical life. Yes?
Your cost that you showed up there, 528 million, was that, it went through pretty quick, so I missed it. Was that just the launch cost to launch the vehicle up there, or was that total mission cost, or?
That's just the cost to launch the hardware once we already
Just
have
launch
the hardware and the fuel.
Did you cost the hardware at all?
No, it didn't. That's even more vague than the math.
Okay.
But we do use cheap components like the upper stage of the Falcon 9, something like that, and module from Bigelow Aerospace, so we're not talking like a really expensive mission. And these things are all.
Is this open source software? Close?
It's the models are only for ours, but you can adapt them for other spaceflight simulations.
I'm just saying, you want to give out the source
Yeah.
code or?
To do that, yeah, it's all pretty simple. It's just applications of high school math, early college math, and all of the information is also on NASA's JPL simulator, which is also free. So.
All right.
Thank you.